Okay, we're going to look at assignment 45. We're going to do problem 16. So it says a 200 kilogram satellite. So the mass of the satellite is equal to 2,000 kilograms. Orbits the Earth. So first of all, because it's the Earth, we need to know some stuff about the Earth. So we know that the mass of the Earth is 5.98 times 10 to the 24 kilograms, and the radius of the Earth is equal to 6.38 times 10 to the 6 meters. So it's an elliptical orbit. Now it has the diagram. So again, we know that in an elliptical orbit, the sun is at one of the foci. It's not in the center. So the speed is not going to be the same. So we have V2, V1, this is 0.1, this is 0.2, and then this distance was R2, and this one was R1. So when it's closest to the Earth, it has a speed of, so V1 is equal to 7735 meters per second, and R1 is equal to 1.63 times 10 to the 6 meters above Earth's surface. So the mistake that I made, again, when you're looking at the Earth, and this is an exaggerated picture from here, you have the radius of the Earth, and then you have the distance, let's say, of the satellite above Earth's surface. So you're going from center of mass to center of mass, so I have to take into consideration the radius of the Earth. So part A says, determine the total energy. Well, the total energy is a sum of the kinetic and the potential. So the total energy is going to be 1/2 mv squared plus negative g, the mass of the satellite, times the mass of the Earth. If you want, usually for the Earth, and I should have done that, you usually make the mass of the larger celestial body like the planet a big M. So let me go ahead and change that, because a lot of times you'll just use little m big M over R. Now the trick here is this R is really the total R here. It's RE plus R1. Okay, so that's the trick there. So E is equal to 1/2 of 2,000 kilograms times 7735 meters per second squared, plus, and a lot of times people just put the negative, but I do it like this so I make sure I don't forget it. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times 2,000 kilograms times 5.98 times 10 to the 24 kilograms divided by, and this is where you can make your mistake, 6.38 times 10 to the 6 plus 1.63 times 10 to the 6. So remember, this radius is, again, the radius of the Earth plus the distance the satellite is above the Earth. So that's where you could make a mistake. So this comes out to be negative 3.98 times 10 to the 10. Now remember, there's a lot of exponents here, so you really need to practice on your own to make sure that you don't make a mistake. Okay? All right. All right, let's look now at part B. Part B says, determine the angular momentum. Okay? So what do we know about momentum? Well, angular momentum is L. So we know that L is equal to I omega. But we also know it's equal to mvr. So we know that mvr here is equal to mvr here. We know that angular momentum is conserved. Now, if you look at this, if I say, now, it said determine the angular momentum at point 1. So L1 is equal to V1R1. So that's going to be equal to 2,000 kilograms times 7735 meters per second times, again, this distance, it's really not R1. I shouldn't have done that. I should call that R total, because R total is actually the sum of the radius of the Earth plus R1. So that's probably where you would be most likely to make a mistake. And now I'm going to add those two. So it's 6.38 times 10 to the 6 plus 1.63 times 10 to the 6. So L1 comes out to be 1.24 times 10 to the 14. Now we have kilograms, I have meters per second, and then I have a meter. So my final unit would be kilogram meter squared per second. And then in part C asks us, it says determine the speed at point 2. So remember, we know that angular momentum is conserved from here to here. Okay. Now, I just found the angular momentum here, so I can find it here. But I'll just go ahead, because if I want to get full credit, I need to show all my intermediate steps. So L naught is equal to LF. So mv1r1 is equal to mv2r2. So remember that the masses can cancel because it's the same satellite. I would go ahead and rearrange my equation to solve for the unknown in terms of the known. So v1r1 over r2 is equal to v2. So I have 6.38 times 10 to the 6 plus 1.63 times 10 to the 6. That's r. I shouldn't have done that second. Times 7735 meters per second divided by 6.38 times 10 to the 6 plus, they gave us the new radius, was at 2 was 5.63 times 10 to the 6. So my final answer for V2 is 5157 meters per second. And again, this is for an elliptical orbit.